Life is hard enough as it is, and I try not to load myself with the things that I don't have to do. But as a physicist, I always find out that sooner or later, and most often sooner, I have to take account of symmetries of the problems I study. It turns out it's a lifelong quest, and depending on what kind of problem that you do, the techniques and concepts from the repertoire of mathematics and physics dealing with symmetries change. So I started out as a high-energy theorist, and like almost everybody who is forced to learn some group theory, I eventually wrote the book. It's a good book. It's original. It's unlike any other book on group theory. And it turns out that techniques are useful in many occasions, and lots of people today use that book. Then I changed the subject, and I was free of dealing with symmetries. I thought I was doing turbulence. It's messy, complicated. What does symmetry have to do with it? Turns out everything you cannot do kind of theory of turbulence we would like to develop without using symmetries. And out of all this, several things came through accumulated experience, which I think are worth teaching. I cannot teach you how to use symmetry in your particular research problem, but I can teach you some universal concepts. Anybody sooner or later has to. Doesn't matter what science is, or aeronautics, electrical engineering, data science, various kinds of physics and biology problems, or the traditional things where you need symmetries, like condensed matter and high-energy physics. What came out of this is, first, and this is what I'll teach you in this course, you have to know your linear algebra. It turns out the linear algebra is always coming back to haunt you, and they're always, centuries after people have invented notion of a matrix and a vector, coming back to haunt you in new, totally surprising ways. For example, in trying to understand how a monkey moves a muscle. Turns out linear algebra is the main tool as a theorist to deal with this and how to apply it. So we will start with some linear algebra, and that will naturally go into the next topic, which is quintessentially group theoretic. It's called theory of finite groups. It has many guises: permutations, rotations, flips. It turns out to have a very beautiful backbone, which you can go through. It just takes several work days or weeks of linear algebra. And the essence is called character orthogonality relations. Now, many of my colleagues who do, let's say, condensed matter physics will tell you they never learned that stuff and they don't need it. That's okay. They use it. They just don't call it group theory. The essence of it, the core, is very beautiful, very doable, very simple. And it says that whenever you have some symmetry, the vector spaces that you work in to describe, now vector space, it just means a finite set of numbers that you use to describe your problems, decompose in something that's called irreducible representations. If they teach you quantum mechanics, they'll never tell you they teach you group theory. But it would be inconceivable to do quantum mechanics without group theory, because you absolutely must go to irreducible representations, quantum numbers, spin states, whatever, to be able to do any calculations, because without it, it's very hard to do quantum mechanics. So when they teach you quantum mechanics, of course, 90% of time, they're just teaching you group theory without telling you that. Most of what you teach in quantum mechanics is not quantum mechanics. Quantum mechanics is H bar. That's the important thing. The phase space is granular. But all the technology is really how you use symmetries to your advantage, how do you group theory. Now, if you continue from this to quantum field theory, it's inconceivable to do it without group theory. And today, every fundamental theory physicist, from cosmology, general relativity, to particle physics and its fancier variants, most of the time does group. Now, that group theory tends to be the next step in our development, of course. It's called theory of continuous symmetries, or Lie groups in more technical jargon. So I'll teach you that next. And that requires, it's still characters and characters orthogonality. So that's an amazing thing that both discrete and continuous groups share. And parts of it you've learned under other names. For example, you've all been taught Fourier analysis. Well, that's the starting point of group theory of continuous groups. But that eventually ends in some amazing and incredible things that group theory brings to you. So when I teach you group theory, I'll first teach you the simplest one, S, or 2 rotations in a plane, then rotations in 3 dimensions and rotations in complex space, because lots of theory likes, that's called unitary groups, lots of theoretical reasons why you need this. An amazing thing happens. It turns out that our space, 3-dimensional space, doesn't actually have 3-dimensional objects as building blocks, but has a 2-dimensional complex objects, spin 1/2. In classical physics, nothing to do with quantum physics, as its building blocks. This comes under different names, quaternions, and you can't do computer games without using quaternions because it's a good way to think about rotations. But that thing goes into relativistic physics, into Minkowski and Poincaré kind of symmetries. It turns out if you understand it in this simple classical setting, you'll be in good shape to understand special relativity, and you'll be able to start thinking about how to do general relativity and particle physics. So this course will end with some very simple examples of how you use group theory. For example, there's something called the eightfold way. And this is one of the very first and very impressive applications of group theoretical thinking to produce prediction and then observe experimentally in particle physics. And we will end up with an example which you hear a lot about, which is basis of standard model, kind of ideas that go into building standard model. So that will be the course. Hopefully, no matter what you do in your research in the future, if you remember just basic concepts of the course, it might come in useful. And if my experience is any guide, you will not be able to do your work without it. So I feel good about teaching this course. I think it's necessary, even though most people who need it most, let's say my fluid dynamics colleagues, never get it and never learn it, or data scientists, for example. That's a good news for you because you'll have a tool that they don't have and it'll serve you well.